Hello, in this session we're going to have a look at the cogging torque and especially how we can mesh it and how we can solve it using Altair Flux. So the agenda today in this short video is what is the cogging torque. So we're going to have a look and see what is this phenomena and where does it come from and why we want to simulate it. Then we're going to see how to simulate it in Flux, so especially looking at the steps to follow in order to build a model and solve it easily. And then we'll do some demos, first on a Flux 2D model, starting from just a geometry and mesh, and we'll add whatever is necessary to solve this model. And then same thing in 3D, starting from a CAD geometry, we'll start to build the necessary air volumes especially, and apply some mesh and repeat the same setup process for the physics in order to do this cogging torque computation in 3D as well. So first, what is the cogging torque? So to give you a definition, basically went to Wikipedia, and this is what Wikipedia says. The cogging torque is mostly the torque due to the interaction between the magnets and the stator slots or stator teeth, depending how you see it, in a permanent magnet machine. So this torque is really dependent only on the number of magnetic poles and number of teeth. So this will generate a given number of harmonics that can be interesting to look at, because this cogging torque is mostly an undesirable component. So it's something you'd like to avoid. You try to get rid of and to simplify as much as possible, especially at lower speeds. And also this cogging torque may end up in also other phenomena but at higher speeds. So you might see some torque ripple or speed ripple, which can create some noise especially, and will also be linked with NVH further down the line. So it's very important to consider this as a first step and be sure to understand it and try to reduce it also. So in particular, the more popular method would be to do some skewing on the permanent magnet machine, whether it's a continuous skew or a step skew, as we can see on the picture below. And you can see the effect of here it's on the ripple torque, but we would have the same phenomena on the cogging torque. We would try to decrease all the oscillation and try to have a more smooth constant value as much as possible for the torque, and almost zero value for the cogging torque if possible. So let's see how we can simulate it. So we can basically follow the different steps I listed here. So first, we'll need the geometry, which is meshed ideally. Like we see here on the picture, we'll probably have the air gap, which is slide into two parts at least. So one part will be rotating, one part will be fixed. And then we can start to define the physics. So as I say in the definition, in the cogging torque, we only have the interaction between the magnets and the steel. So in magnetostatic, we just need to create materials for the magnet and the steel. We create some fixed part and rotating part. Then we can assign the correct regions to the moving part and to the stationary part. And we need to define a scenario. So I will come back to the scenario definition. Then we can solve. So because if we use magnetostatic, it will be just a list of independent steps. There's no transient happening here. You can solve it in transient, but I would say it can be much faster if you do it in static. So if you solve in static, you can use also distributed computation to run on multiple cores as much as possible and save time. And then once your project is solved, you basically plot the curve of the torque, and you can also do the FFT to get more in depth of the analysis of this cogging torque. So to come back on the scenario and the time step to adopt, in particular the scenario for the cogging torque is important. In most cases, because you will have something periodic, we can basically solve just one slot pitch. If you move one slot, then you will be in the same position as you were at the beginning. But sometimes, like in the picture here, you will need to solve a much longer scenario to get really the detail of the cogging torque, because you may have additional things going on. For example, if you have housing which is not circular and periodic, if you have some holes somewhere, if you have some slits, like you may have sometimes in front of the teeth, so a square lamination like on the picture, or if you want to look at the cogging torque with the eccentricity, then for all of these cases, you will need to solve for a full turn with a very small time step. Okay, now let's have a look at the Flux 2D demo of geometry and mesh. So we'll start from an overlay model, which is the geometry we see here, and we'll try to follow the different steps that I gave you earlier, and we'll see how we can even refine this cogging torque computation by adding 3 layers air gap and some mapped mesh in addition. So let's switch to Flux now. This is my model. This is just a geometry, which is also already meshed. Okay, so built from the overlay. And now what I need to add is all the physics and all the cogging torque definition ready to it. So I can go in application. I'm defining a magnetostatic application. All right. The depth of the domain is 75 millimeter. And now I can start defining the physics. So first thing we need would be materials. I can go into the material manager, and I will need to import 2 materials here. So the material for the laminations, which are on the rotor side and on the stator side, and the material for the magnets. So for the lamination, we're going to take this material, the M270, and for the magnets, we're going to take this one, the N35. Okay, so we're good. We have our 2 materials. Then we can define a fixed and a rotor mechanical set. So let's start with the rotor. The rotor is going to be on 0, 0. Okay, and let's create the stator as well, which will be fixed. Okay, and now because my regions already exist, because I used the overlay, I just have to assign the correct physics to all of the regions. So there's a lot of air region at first. So for example, on the air gap, these 2 are just air region. I can just define them as air and belonging to the rotor. Then I have my laminations here. So these will be laminated with the cogent material. I put the correct thickness and the stacking factor for my laminated material. All right. Then I have my 2 magnets. So these 2 will be defined as magnetic using the magnet material, and also put on the rotor. Okay, then we have all the stator materials. Yes. So this one, this one, this one will all be air region, air, and then stator. And just the lamination will be the only different region we have on the stator side. And here we go. So we assigned the regions. Now we can just orient the magnet. So here we have directly a coordinate system for the magnets in the middle, so I can just orient them very quickly. And now I can prepare my scenario to solve. So I can create a new scenario in which I will actually move the rotor angular position. I can also activate the parametric distribution now, which will use our multiple cores to solve even faster. So here we'll solve from 0 to 7.5 degree, which is 1 slot. And we'll put a linear number of steps with 41 steps. So that means we'll have 40 steps on one period, basically. And that's good. And now I can just solve this model. Okay, now my model is solved, and what I need to do to post-process it would be to plot the curve. So I can plot the Cogging torque this way, plotting the curve, and okay. I have a nice smooth curve of the Cogging torque. I can have a look at the FFT. I can do right click here and display the FFT. Let's say 16 harmonics. And now I can see the spectrum of my Cogging torque, all right, with all the different harmonics. So this is what I would do in general to do a Cogging torque in 2D. And we can see here it's using the overlay mesh, but even in general, the mesh from in 2D, even the automatic mesh will give pretty nice results as long as you have these two elements in these two layers in the air gap. You will have a really nice shape of elements, so it should be okay for most of the cases. But in some cases, you may want to have even a thinner mesh than this. So you can go ahead, delete the results, and you can start adding a third layer. So if I go in the sketcher and I remove this one, I just replace it by a line for now. And I will go here and remove as well this point, just make it a single line. And now I will draw one more layer in the air gap. So I'll try to put it like 1/3 of the thickness. So I draw a new arc. I start somewhere here, let's say here, up to the other side. Okay, and then another arc. Starting here and then going up this way. Okay, I can heal the geometry just to make sure everything is fine. I can go out. I can complete the infinite box again just to make sure the mesh will be periodic. I need to reassign this region to stator air. And now I have these three faces that I need to reassign to something. So let's say, for example, this one would be the rotor air. This one would be the stator air, obviously. Stator air gap, same. And the one in the middle can actually be on either side, it doesn't really matter. I put it on the stator air gap. So now we can see we have three layers. And the important thing we need to do is to define a different mesh for this face. So if we edit this middle face, put it as a mapped mesh, it means that now it's going to put square elements in this one, but we need also to control the number of elements. So we can select these two lines, say edit, and then as a mesh line here, we can add a new mesh line, which will be arithmetic, which means it's a number of elements. So here, if I want 40 elements on one slot, I have 6 slots, so that makes me 240 elements on the whole for 6 slot length. Okay, I can apply this, and now I can try to mesh. Okay, and now we can see the mesh. So we have approximately the same size of mesh as we had before, but now we'll see after solving the result if we use this one instead of the other one. I already have this model solved here. This one. Okay, so what happens is that we have this mesh, and one time step is actually equal to exactly one element. So if I switch to the first time step, you will see the rotor has moved exactly one element. And this is important. So if you have a really difficult result or it's something very, very sensitive, using this method, you will have less interpolation between the nodes. It will be as if it jumped from one node to the next, and it makes the numerical noise very, very reduced as much as possible. So that's the method you need to use if you have a very difficult Cogging torque to compute. and you can apply this in 2D models, of course, and we'll see how we can do it in 3D models as well. To give you another reference, so here was the cogging with a refined mesh. It's slightly smoother, but there's not a big difference because the first one was already good. But to give you another comparison, on purpose I made a really bad mesh. So if you look here now, that's the original geometry with 2 layers. And what I've done is I forced these lines in the air gap to have really large elements. So we can see the triangles are very squashed and the mesh is really a bad quality. And now if we look at the results with this really bad mesh, so let's plot the cogging again. And now you can see the impact of the mesh. So if we compare again this one, which is the refined one, which is very smooth, and this one, you can see it's very noisy. The amplitude is 7.5, 7.8. It's not even symmetrical. Here we have 7.8, and here we have 7.85. So it's exactly symmetrical. It's very good. So this was the 2D example, how to do it in 2D. We've seen how we can set it up and how we can change the mesh to make it slightly better. Now let's look at the Flux 3D geometry and mesh and see the difference. So this time I will start from a CAD import, as you may have sometimes. I will add some sliding cylinders, I will do an assembly, I will repeat the 2D setup quite quickly, and I will add some extrusive mesh as well to save elements, especially in 3D. Okay, so I'm in a new Flux 3D project. Let's start by importing my geometry. So here is my geometry model, and I can see that I have all the solid parts, but I don't have anything for the air gap. I don't have any sliding cylinder. So let's try to create quickly a sliding cylinder. So it's important to have layers of air in the air gap, but also on top of the model. Let's do 2 more cylinders. Let's just assemble them, and then I will cut them to have just the part that I need. So now I have a few different objects. We can see some superimposition. I just need to assemble everything together. Okay, and now we'll see we have all the rotor parts. We have a layer of air on top. We have our 3 layers of air in the air gap, and we have all the rest of the stator here. That's good. We can close the modeler. Okay, and I can start defining a magnetostatic application already. So here I need to add still the infinite box and periodicity. So let's do that now. And now I can complete the infinite box, which will close the missing faces and will also define a linked mesh on both sides of the machine. Okay, very good. So now basically the geometry part is done, and the next part would be to do the meshing. So what we can do in order to define an extrusive mesh can be to select all the volumes. This one can have an extrusive mesh. So I could go ahead, mesh, create a new mesh generator. This one will be called extrusive, and it will be extrusion type. I need to associate a transformation with this extrusion. So it's, let's say, Z extrusion. And it needs to be the same length as the extrusion I made in the modeler. Okay. So I create the extrusion, I use it in the extrusive mesh generator, and then I assign this extrusive mesh generator to these volumes. And now something important, I need to control the number of elements I want on this height. So I can select a single line, like this one, for example, and I will create a mesh line to control the number of elements I want along the height. So let's say, for example, I want 5 elements, then this forced 5 elements here will force 5 elements on all the layers everywhere. Okay, and then one last thing we need to do in order to have the same mesh as we had in 2D. We have this face in the middle. So this is going to be extruded, but I also want it to be mapped to have the rectangular element as well. So I can go on this bottom face, mesh, and apply the mapped mesh. And again, as I did in 2D, I can just edit these two long lines and give them a different number of elements. Now, if I click on mesh, okay, so we have our 5 layers of elements. And if we look again at the middle lane here we have 3 elements which are extruded, so it's like a penta element. And here we have square elements, and one element should correspond exactly to one time step later on. And now that my mesh is done, I can basically reproduce the same setup I've been doing in 2D, which is importing materials, creating regions, and assigning all of this. So let's speed this up. Okay, so now my model is defined exactly as in 2D. I have the same magnet orientation, the same lamination material for both rotor and stator, and I define mechanical set exactly the same way. Now I can define the same thing as before, which is the scenario. And let's solve this one. And here is the solve project. So now if we plot the curve again, we'll get this very nice, smooth, and very good cogging torque, which looks exactly like the one we had in 2D with the refined mesh. So this is a very good 3D model and really good mesh. On the other hand, if we go ahead and just mesh the whole thing without looking at the mesh, without putting really nice free layers mesh and so on, here's an example of the torque you could get. So you see the torque is just negative, it's completely wrong. And just to explain to you the difference between the two models, so this one is exactly the same model that I prepared before, but I removed all the mesh information with the layer mesh and the exclusive mesh, and I basically just applied the aided mesh, the default mesh that Flux will create. And you will see Flux will manage to mesh well the very thin layers of the air gap. It will mesh small elements on the side, but it will make a large relaxation on the whole air gap face on the stator and on the rotor as well. So this very bad mesh, which is not the same along the air gap, which is not the same along the height as well, this is going to create very, very bad results, especially for the cogging, but also for any type of simulation, really. So that's why it's important to have the correct geometry and the correct mesh definition to do any of this computation. So now let's see the conclusion of this Ask the Expert about the cogging torque. So we've seen we can easily define a workflow and define quickly the different regions we need, so mostly magnet, lamination, and the rotating bodies. We've seen the geometry of the air gap is important, so having 2 or 3 layers will change a lot the model you will solve. And also the most important part is really the mesh. So we've seen a really bad mesh can give you completely wrong results or very noisy results, at least in 2D. And using exclusive and mapped mesh can be really necessary and can save you a lot of time and memory actually by having a very regular and nice mesh in the air gap.